My name is Ganesh Balamurugan, and I'll be talking about link budgeting and modeling as they relate to high-speed wireline links. So if you look at the wireline scaling trends over the last couple of decades, the per lane data rates have been increasing at a steady clip, roughly doubling every 3 to 4 years or so. So today in 2019, 28 gigabits per second solutions have been deployed, 56 gig solutions are starting to be deployed, and many 112 gig solutions are in development. Now, to design robust and reliable links that meet our bandwidth and bit rate targets at these rates, accurate link budgeting and modeling is becoming increasingly important. To see what this entails, let's look at an example data center link. So what's shown in this figure is a wireline link connecting two switch ICs that are sitting in separate server racks, which in today's data centers may be several hundreds of meters away. So they're connected through a long single mode optical fiber, and they plug in to the server rack itself through these pluggable optical modules, which house the optical transceivers. So if you look at this link in a little more detail, in the schematic view that's shown here, which shows the switch ICs on a package sitting on a PCB, talking to the optical transceivers in these pluggable optical modules. And then the data goes over this long single mode fiber, and then we have the corresponding receiver circuits on the other side. So we can notice that there is actually two distinct links, a relatively short, maybe a few inches long copper link between the switch IC and the optical transceiver, and a longer optical link between the two optical modules themselves. So what link budgeting entails is dividing the available SNR budget that the standard specifies. So the standard specify things like the target baud rate, modulation, and beta rate, and so forth, which translates into an SNR budget. And for link budgeting, what we want to do is see how do we divide that available SNR budget between the different link impairments that the signal faces. So for example, on the electrical link side, we want to see, okay, how much of that budget do we allocate for the insertion loss that we incur as the signal travels over these copper traces, how much should we allocate for a crosstalk, and so forth. Similarly, on the optical link side, we want to see, okay, how do we allocate the available budget between losses we incur in the optical modulator, losses we incur in the fiber, and so forth. So on the electrical link side, where the problem is a little more complicated, the channel operating margin, or COM, as it's commonly referred to, has been adopted as sort of a standardized way to do this link budgeting exercise. So in the next couple of slides, we'll see what channel operating margin is and how we can use that to budget electrical links. So channel operating margin, or COM, is actually nothing but signal to noise ratio metric as defined in this eye diagram plot shown on the left. So from the eye diagram, we can extract sort of what the average signal energy is, and that's referred to as this A subscript signal. And the eye diagram, by also looking at the contours of the eye diagram at different bit error rates, we can identify sort of at our target bit error rate what's the maximum noise that is riding on the signal. So that's this A noise crosstalk term that's shown here. And by taking the ratio between those two and converting it to a dB number, we arrive at the COM metric. And what this allows us to do, since this eye diagram includes both SERDES and channel specifications, it allows us to tie everything together into a single number. And the way so most of the subtleties in the COM calculation are embedded in this reference model that is used for computing it. So over the years, IEEE has developed a sort of standardized reference model that everybody uses to get consistent COM results. So that is the standardized reference model is shown on the right here. It includes abstractions of key elements on both the SERDES side and on the different components in the channel. So on the transmitter side, we have the transmit feed-forward equalizer, and on the receive side, we have receive equalizer, jitter, and other impairments. And the channel itself includes not just the physical channel itself, but also models for the packages on the transmit side and the receive side. So the details of the COM calculation are in a reference that I've included at the end of the presentation. But at a high level, what the calculation entails is a full statistical analysis of the system in order to derive what these received signal distributions are going to be after the signal passes through all the elements that are shown in this reference model. And once you derive those distributions, the computation of COM is actually pretty straightforward, as shown in this formula. And most standards require a COM of higher than 3 dB to qualify a particular budget or budgeting scenario. To understand this a little better, let's look at an example, a result of such a calculation. So the graph here shows the received signal distributions starting with no impairment besides the pure channel loss. So this is the dotted line shown on the two ends of the graph. And then we progressively add the different impairments like crosstalk, intersimple interference, jitter, noise, and so forth, which progressively pushes the curve more towards a signal threshold of 0. So from this plot, we can derive the signal and the noise components as shown here. And in this case, the signal component is around 35 millivolts. The noise, which is the difference between that signal and so the maximum, the minimum signal we receive at the target bit error rate is around 22 millivolts. And so taking the ratio of those two and converting to dB, we get about 4 dB of COM, which is greater than our 3 dB target. So the scenario shown here would be considered sort of an acceptable link budget. Now we can do a similar breakdown for the optical link budget as well. So an example is shown here for, let's say, a 400 gig DR4 optical link. So this would be, this could possibly be the budget for that long optical link that we showed in the example earlier. So here, one might start from sort of the available optical power on the transmit side, and then you progressively add the penalties introduced by the different impairments. So for example, in this graph here, the first penalty that's added is the PAM4 penalty, which reduces the signal strength by about 1/3, and so that's the 4.8 dB reduction. And then we add the penalty to the channel loss, which is around 3 dB due to multipath interference, and then finally due to all other transmit impairments like bandwidth limitations, nonlinearity, and so forth. And so adding up all these impairments and subtracting them from the available transmit power gives us sort of the minimum receiver sensitivity or the minimum power our receiver needs to be able to resolve in order for the link to operate reliably, which in this case around -9, a little over -9 dBm. Of course, we could do it, go through the exercise the opposite way too. For a given receiver, we can, with a given receiver sensitivity, we can add all the penalties to figure out, okay, what should be the available transmit power need to be in order to achieve the same target bit error rate. So one can do it both ways, and really the optical link budget is just a list of the breakdown of the different sort of loss mechanisms in the optical link. Okay, now I'm going to switch gears a little bit and talk about the link modeling aspect in wireline links. So again, if we go back to the example data center link that we had before, what link models do is, again, help us abstract the different components of the link, the SERDES in the switch IC and the optical transceiver and the channel and so forth, similar to what was done for the COM model, but in a greater level of detail, so as to allow us to define some architecture specs for the SERDES. So some classic examples of this could be the equalization architecture in order to achieve the target bandwidth and bit rate for this electrical link between the switch IC and the optical transceiver. Like, how do we divide that equalization between the switch IC and the optical transceiver? What kind of equalization to use, what kind of ADC, DAC resolution to use, and so forth. So link models allow us to define some of the key aspects of the SerDes architecture. They also allow us to translate sort of higher level specifications that are specified in the standards into lower level circuit level specifications like PLL jitter, the clock distribution, jitter amplification, and the TIA noise, and so forth. Of course, they also allow us then to validate end-to-end link performance at a much greater level of detail than what the COM models do. So over the years, people have looked at several methods in order to analyze links. There's been work on statistical analysis of links, which essentially does a rigorous probabilistic analysis of the signals at various points in the link, assuming that all the link components are linear and time invariant. And then there are time domain simulation models which use more general behavioral models of the link components and use of standard simulation tools like MATLAB to do time domain simulation of the link themselves. And then there is refinements such as event-driven simulation, which help to speed up the simulations without sacrificing too much accuracy. And finally, there are industry standard models that are used to abstract the link components so they can be shared by different vendors to do end-to-end link validation. So in this presentation, I'll focus mostly on the time domain simulation, since that's what's used by most designers, especially in the 50 plus gigabit per second regime, where it's very important to account for non-idealities such as component non-linearities, and the bit rate targets are relaxed to the point where a full time domain simulation of the link is indeed feasible. So let's look at what some of those time domain models would look like for different components of an electrical link. So here I'm sort of showing a high-level overview of what are the different components in an electrical link. And broadly, they can be divided into three categories. There are a set of components that constitute the transmitter, a set of components that constitute the receiver, and then the channel in between. And as we'll see later, we can use a mix of time and frequency domain representation for these different components. One important thing to note is for the channel modeling aspect is that it's very important to include the crosstalk channels, since this is kind of increasingly important effect in the context of like high-speed multi-level signaling like PAM4. And typically the crosstalk channels are assumed to be asynchronous with the main channel. So the next couple of slides, I'll show some details of the transmitter model and the receiver model, followed by some examples of how these models are used or what kind of analysis these models enable, and show some example results. Okay, so here we show some details of the electrical transmitter model. So the picture on the top is a block diagram of an actual high-speed transmitter implementation, including everything from equalizers, serializers, details of the clock distribution, and the output driver and matching network. The model, we abstract a lot of these details into a few blocks. So we have a linear or like an FAR filter to model the feed-forward equalizer, a DAC to model the finite quantization error introduced by the output stage, followed by some kind of a nonlinear compression circuit, since all real drivers have some signal compression. And then it's also very critical to model the output network, since that has a significant impact on the overall channel bandwidth. And the other aspect of the transmitter model is the clocking model. So that is modeled, rather than modeling the actual clock waveforms, we extract a jitter sequence that reflects the characteristics of the statistical behavior of the jitter from our clocking circuits. And so we include elements such as the PLL, the jitter amplification through the clock distribution. And once we compute the resulting jitter sequence, we can convert that to sort of equivalent voltage noise and add it to our sort of idealized zero jitter transmit output to get the actual transmitter output. Here's the corresponding picture for the receiver side. So on the top again is a block diagram of an actual 112 gig receiver, including the input matching network, the analog front end, followed by ADC and the DSP, and the clocking loop closed through a CDR. This is abstracted again with a mix of time and frequency domain models for the different blocks. The input network and the analog front end are typically defined in the frequency domain. Again, similar to the transmitter, we add a nonlinearity block to model the signal compression in the receiver chain. Following the receiver front end, we have the ADC modeled as sort of an ideal quantizer with some input sampler noise and also some input jitter through the CDR, where the jitter is converted from the jitter sequence to a voltage noise using techniques very similar to what we do on the transmit side. So here are a couple of examples on how we can use these models, or how designers typically use these models to make design decisions. So in this example, we are using the models shown before to figure out how much equalization should I do on the receiver side in a receiver DSP, and what resolution should my DSP have. So using the models shown before, we can generate results like what is shown here on the plots in this slide. So on the left, we show so how does our voltage margin at a target bit error rate vary as we so both increase the number of taps in our receiver side equalization, and for different divisions of those taps between precursor and post-cursor taps. So using this, we can decide what's the optimal number of taps we want to achieve, allocate for receiver feed-forward equalization, which in this case is around, say, 12 or so. And the plot on the right shows the sensitivity of performance to the resolution we choose for a DSP. So of course, we want to choose the minimum resolution we want that is required to meet our target bit error rate for power and area efficiency reasons. And an analysis like this shows that, shows what that number needs to be, which in this case is around 8 bits or so. Again, we can do a similar analysis to figure out what kind of specifications our ADC needs to satisfy. So here we can see, how does my ADC resolution and my receiver input noise impact my overall link voltage margin, and study what kind of trade-offs do I make in order to optimize overall power. So I could either go with a higher resolution ADC and a higher noise but lower power analog front end, or go with a lower resolution ADC and a lower noise but slightly higher power analog front end, and compare those two scenarios to figure out which one gives you sort of the most optimal or lowest cost implementation. Another example here to illustrate sort of the utility of link models for link design. Here I'm showing how does my voltage margin vary as a function of linearity of my analog front end. So this is important, especially in the context of like PAM4 type signaling, or anywhere where we need to do heavy equalization beyond the analog front end. The linearity of the analog front end is obviously critical. However, improving the linearity typically comes at a steep power cost, especially beyond a certain threshold. And so an analysis like this can help figure out what's the minimum required linearity spec. And so in this case, we could convert the overall link level specifications into a block level specification, like the third harmonic distortion for the analog front end, in order to provide component level specification for the block designer. Okay, so to summarize, I think it's becoming increasingly important to have very accurate link budgets and models in order to build efficient but robust high-speed wireline links. And we saw how the channel operating margin, or COM, is a way to do link budgeting in an efficient way, and also in a fairly standardized way, so it can result in consistent results across the board. And typically, more than 3 dB of channel operating margin is considered acceptable. And then on the link modeling side, we saw how we can use behavioral models for different components of the link with a mix of time and frequency domain representations to guide SerDes architecture definition and link validation. So finally, I want to acknowledge the help from my colleagues at Intel, Ajay, Shiva, and Frank for their contributions to this presentation. Thank you.